Hi, Chem Gang. You've watched the video that tells you that ocean acidification is a big problem. So this voiceover video activity is going to help you see the chemistry behind it. All right, take a look at this graph here. And the first thing I'm going to have you do is tell me what you think this graph shows. So hopefully you pointed out the following things. It's measuring atmospheric carbon dioxide at a specific location, which is the Mauna Loa Observatory in Hawaii. And this is recent history, meaning about a 45-year period leading up to 2008, I think is when this graph was made. If you didn't already comment on this, stop and comment now why there's a blue line and a black line here. Why do you think? So we've seen this kind of idea in modeling before. The blue line is the actual data, and you see there's a cycle here. And if you look carefully at the scale down here, there are 5 peaks every 5 years. This is clearly showing something that's a yearly cycle. The black line, however, is the average data. So it takes out the yearly cycle. And so what you're seeing is every year there's an increase and then decrease in carbon dioxide. And take a quick moment to think about what might be a reason for that. The answer to that question is it has to do with the growth cycle of plants. So carbon dioxide is taken in by plants when they're growing, and it's actually a significant enough effect to change the carbon dioxide levels in the atmosphere. So the oscillations in the blue line are really indicating the cycle of the growing season in this area. All right. What's most important to us, however, is what this carbon dioxide is doing to the oceans. And if you look down here, you'll note we are not talking about carbon dioxide causing global warming. That's a separate idea that we've already covered. So carbon dioxide leading to ocean acidification is another topic that also causes great concern, and we're going to get into the chemistry behind it. In order to understand that, you need to know a little bit about pH, and we're going to learn a lot more about pH later in the chapter. But it says right here, pH is a logarithmic scale, and this is actually an error. It doesn't go from 0 to 14. It can actually go below 0 and above 14 because logarithmic scales don't have a beginning and an end. They're the power of 10 scale. And what you probably really need to know about pH for now is that 7 right in the middle represents something neutral. And the lower the pH, the more acidic the solution is, and the higher the pH, the more basic it is. And you know a little bit about what makes acidity and basicity, but we'll learn a bunch more later in the chapter. All right. This little exercise is designed to show you that various liquids that we're familiar with end up in very different places on the scale. So a glass of drinking water should be neutral, kind of right in the middle. These are the oceans themselves. The oceans actually aren't neutral, even though they're water. They're slightly on the basic side. Really acidic things would be things like battery acid, and really basic things would be things like drain cleaner. Right. You probably know that orange juice is acidic. People often talk about that, or the citric acid. What you might not have known is that Coca-Cola and sodas can be quite acidic. So that belongs right there. And some household products you've already learned that feel slippery, which would include bleach and ammonia, would be on the basic scale. So let's see, I think bleach is the more basic, and there's ammonia. All right. So just know about acidity, basicity, and 7 being in the neutral for now. All right, so take a look at this graph, and what is this graph showing you? So you should have mentioned that this graph is tracking the pH of the oceans, it says right here for the ocean, over the last about 20 million years. Notice these are millions of years. So these are long-term averages that scientists have measured through various interesting means. Right. What's more important, though, is what's going to happen over here. Right. So this is actual data from the last couple hundred years and projected data over the next 100 years or so. So watch what happens when I go over the various numbers and then make a statement of what you think that is showing. What's the importance of what shows up right now? All right, so now's when you're going to make your statement. All right. All right, so what you're seeing here is really rapid change. And I apologize, when I move the cursor, the numbers are going to disappear. But when I go over here, you saw a vertical line going straight down. That means there's been a change in pH without any change in time. In other words, on the sort of geological time scale of the oceans, this has occurred in the snap of a finger or no time at all. And any of the changes that have occurred in the past have occurred on a slope, which means it's taken millions of years to make a change from here to here. But if I go back over here, you can see a similar change occurring in essentially 200 years, which is nothing compared to several millions of years. So the thing that we're most concerned about with these changes in the ocean is not that the pH is going down, because it's gone up and down before, but it's happening so rapidly that there's going to be no time for organisms to adapt. Right. There's also a very important note on the bottom. I mentioned the logarithmic scale before, so just take a moment to remind me what you know about the logarithmic scale. So you should have mentioned that the logarithmic scale is based on powers of 10. And that means every time you go up a unit on the scale, you're actually going 10 times more. So we don't actually see pH 7 and 8 on the scale, but a pH of 8 is 10 times more basic, essentially, than a pH. Let me use 9 and 8. A pH of 9 is 10 times more basic than a pH of 8. And we'll talk about what it's actually measuring on the pH scale when we get there. And what that means is when you have what appears to be a small difference, 8.2 to 8.1, if you're thinking about your grades, what's the difference between a grade of 82 and 81? They seem almost the same. You really wouldn't care very much. Okay? But you see here on the pH scale, this is a 30% increase. And they said in acidity here, it's actually in something different that's measuring the acidity. But 30% is a pretty large effect. That's like the difference between getting an 80 on the test and like a 56 on the test. So, these logarithmic scales are designed to show larger changes, so even smaller changes on the scale are pretty important. All right, now we get to the real hardcore chemistry stuff, and we'll have to take a few minutes to digest this information. But the first thing to note here is that there's a whole bunch of reactions with double arrows. Okay, what does that mean to you? So these are representing a whole bunch of different chemical or physical changes, as we'll see, which are reversible. Okay? And that means these can reach equilibrium, and equilibrium is going to be involved. So that's going to be a really important point here. All right. Let's take the first change up here, because this one's actually really important. So these arrows, what change that we've learned about do they represent? Try to represent it in just a couple of words. So this is the dissolving of carbon dioxide in the ocean. Okay, it's carbon dioxide in the air and carbon dioxide in the ocean. So this is a physical process that we just talked about, but it reaches equilibrium. And we actually talked about this when we talked about the feedback systems for global warming as well, because when there's more carbon dioxide in the air, there's going to end up being more in the ocean. So that can help to reduce the amount of carbon dioxide in the air. Okay, we're not worried about the global warming aspects now, but what happens to the carbon dioxide in the ocean? And so what we see here is a number of chemical reactions that occur. And the first thing that happens is the carbon dioxide combines with water to make carbonic acid. And right away, that makes you think about acidification. But as we learn more about acids coming up, we'll learn that it's not the acid itself that really makes the acidification. It's when the acid breaks into hydrogen ions. And there are a couple of steps where that happens, that's shown here, because carbonic acid has two hydrogen ions. So it can give off one hydrogen ion to produce bicarbonate, and if that further releases hydrogen, it'll eventually produce carbonate. And so those are two separate chemical reactions that are actually in equilibrium. Technically, they're Bronsted-Lowry reactions, but we haven't shown the full reaction here, just the key points. And the carbonate that's created is extremely important because carbonate is the key mineral for corals making their shells. And you might remember we talked about that when we talked about the carbon cycle, that the carbon, quote, that is stored in the ocean comes in two forms. One is the dissolved carbon dioxide, but over the longer term, that gets turned into the shells of various types of sea creatures, usually as the mineral calcium carbonate here. All right. And over time, when those organisms die, it falls to the bottom, makes sediments, and gets turned into rocks. So carbon then gets pulled into the rock cycle as well. All right. So here, in essence, is the effect of increased carbon dioxide in the air. The first thing it's going to do is it's going to increase carbon dioxide in the ocean. And it's a little hard for me to stop the video here, so I'm going to have to kind of I can't really point and talk at the same time. But when I put this up here, this is talking about normal conditions, and then it's going to change to acidified conditions. So if you keep your eye on the screen here, it's just going to oscillate between normal conditions and acidified conditions. Okay. When it changes, I want you to look at what's happening with these arrows. What happens is some of the arrows are getting thicker. And when an arrow gets thicker, that means you're shifting equilibrium. Okay. And if you look at the directions of the arrows, you see that the arrows are going to be directed towards bicarbonate here. All right. So let me go over here again so you can see those shifts. Watch the arrows get thick there, they're thicker, and you see arrows pointing towards bicarbonate. Okay. And most important, at the bottom of the container here, if I do it again, oh, actually I can activate that. This means that arrows shift away from calcium carbonate and calcium combining with carbonate. That means there is less acidification, or sorry, less calcification of the minerals in the sea, and you can actually start dissolving the calcification or the shells of the sea creatures. All right. And without the protective shells, there's all sorts of sea creatures that are susceptible. Right? And that's what's changing the ecology of the ocean. So it's when I shift this arrow here, getting thicker, is taking away from the calcification of the sea creatures. And it's related to the carbon dioxide being put into the ocean and then essentially ionizing into bicarbonate. So that's, without explaining everything in great detail, because there's a number of complicated reactions, it's a shifting of equilibriums that dissolves the carbon dioxide and shifts away from calcium carbonate in the sea creatures. All right, and here's one more model. I just want you to take a look at what's happening here. This number one gives actual numbers for the values, and you probably want to keep your eye on pH and carbon dioxide in the ocean, and this, which is a picture of essentially how calcified the coral is. Right? And there's three scenarios here. One is an optimistic scenario. And the first thing that it does is it tracks what's happened in the last approximately 150 years based on real data. So I'm going to scroll through this, and I want you to think what's happening to the amount of coral, what's happening to the amount of coral, the amount of carbon dioxide, and the pH. So I'll go through that. You can replay if you need to. So think about what happened to amount of coral, amount of carbon dioxide, amount of pH. And now look what's going to happen in the future in an optimistic scenario. So again, what happened to the amount of coral, the amount of carbon dioxide, and the pH? Okay. Now we're going to look at a second scenario, which is a middle ground. So remember, modeling has lots of parts to it. And you never know when your model is going to be correct, but this is the middle ground of the different models that have been created. So I'm going to go all the way to 2090, which will include the past history and then the projected changes. So these past changes should be the same, and then look at what's happening in these future changes. And again, think what happened to the amount of coral, the carbon dioxide in the ocean, and the pH. Right. And there's one more scenario here. Let me move this down. This is the worst case scenario. So of the models that have been done, this is the one that comes out to have the greatest effect. So again, the historical changes here should be exactly the same, but here's where the changes occur in the future. Okay. So what do you notice here about the amount of coral, amount of carbon dioxide, and the pH? Mm-hmm. So that's the results of the modeling here. That's about all the time we have for in this video. There is a PowerPoint that has some other information on how it affects sea creatures, so I'll let you handle that separately. Bye now.